Now, the integers under addition is an example of an infinite group since there are an infinite number of elements. In the set of integers, and as some of you may already know, the cardinality of the set of integers is the same as the cardinality of the set of positive integers, which has or is assigned the special transfinite number aleph null, which we will not spend a lot of time talking about cardinality, except to make the distinction between an infinite set and a finite set. So a new definition: a group consisting of a finite number of elements is called a finite group. The number of elements in the underlying set is called the order of the group, and is denoted using the symbol for the cardinality of the underlying set G. So let K be a positive integer. Then from number theory, we know that for every integer n, that integer can be expressed as the sum of a multiple of the positive integer k plus a number r for some integer m, where the number r is an element in the set of integers from 0 to k minus 1. Now this is essentially a restatement of the Euclidean algorithm, and you may be familiar with it and may think of the number r as a remainder, and for positive integers this coincides, but we will call it a residue, and the set of consecutive integers from 0 to k minus 1 is denoted with the same symbol for the integers with a subscript k, and we call this the set of integers modulo k, and this set consists of a complete system of residues modulo k, that is, every integer is congruent modulo k to exactly one of the elements in the set of consecutive integers from 0 to k minus 1. So let's define what we mean by congruent modulo k. Let a and b be two integers, and let k be a positive integer. Then the integers a and b are congruent modulo k, and this is denoted. A is congruent to B modulo k. If and only if the difference, A minus B, is an integer multiple of the positive integer k. So for example, the number 7 is congruent to 1 modulo 3, since 7 minus 1 is 6, and this is an integer multiple of the number 3. And further, the number 7 can be expressed as the sum 3 times 2 plus 1, where 1 is the residue, and the number negative 7 is congruent to 2 modulo 3, since negative 7 minus 2 is negative 9, and this is an integer multiple of the number 3. And further, negative 7 can be written as the sum 3 times negative 3 plus 2, where 2 is the residue. So let the set of integers modulo k be the set of consecutive integers from 0 to k minus 1, and define addition modulo k by a plus sub k, the element b, is equal to r, a residue r, where r is an element in the set of integers modulo k, such that r is congruent to the normal sum a plus b modulo k. Now, notice that this sum modulo k is well defined or uniquely defined, since the number r is exactly one of the elements in the set z sub k. Then the set of integers modulo k, together with addition modulo k, is a finite abelian group of order k. Now, notice that I'm making a statement about an infinite number of groups, so I'm going to be very thorough in the proof of this statement. So proof, let A and B be two elements in the set of integers modulo k. Now, since A plus B is an integer, this integer A plus B can be written as the sum of a multiple, an integer multiple of k, plus a residue r for some integer m, where the residue r is an element in the set of integers modulo k. And so we have that the sum a plus b minus r is an integer multiple of the positive integer k, and hence r is congruent to the sum a plus b modulo k, and thus the sum modulo k of the elements a and b is an element in the set of integers modulo k. Further, since the normal sum a plus b is the same as the normal sum b plus a, the number r is congruent to a plus b mod k and is congruent to b plus a mod k. And so the sum modulo k of b and a is this element r, which is the same as a plus b modulo k. And hence addition modulo k is both closed and commutative over the set of integers modulo k. Now let a, b, and c be three elements in the set of integers modulo k. Then a plus modulo k, the sum or the quantity, b plus modulo k c is a plus modulo k r sub 1, where r sub 1 is an element in the set z sub k, such that r sub 1 is congruent to the normal sum b plus c modulo k, and the sum a plus r sub 1 modulo k is equal to r sub 2, where r sub 2 is congruent to a plus r sub 1 modulo k, and this is the same as a plus the quantity b plus c modulo k, which is simply a plus b plus c, since in for the integers under normal addition we can disregard the grouping. So that is the sum modulo k of the element a plus the quantity b plus c modulo k is equal to r sub 2, where r sub 2 is an element in the set of integers modulo k, such that r sub 2 is congruent to the sum of the three elements a, b, and c modulo k. Now similarly, the quantity a plus b modulo k plus c modulo k is equal to r sub 3 plus c modulo k, where r sub 3 is an element in the set of integers modulo k, such that r sub 3 is congruent to the normal sum of a and b modulo k, and r sub 3 plus c modulo k is the element r sub 4, where r sub 4 is congruent to the normal sum r sub 3 plus c modulo k. And this is the same as the quantity a plus b plus c mod k, which is the same as the sum a plus b plus c mod k. That is, the quantity a plus b modulo k plus c modulo k is equal to r sub 4, where r sub 4 is an element in the set of integers modulo k, such that r sub 4 is congruent to the sum a plus b plus c modulo k. So since r sub 2 and r sub 4 are both elements in the set of integers modulo k, such that r sub 2 is congruent to r sub 4 modulo k, we have that r sub 2 must be equal to r sub 4. And hence the sum of the quantity a plus b modulo k plus c modulo k is the same as a plus the quantity modulo k of b plus c modulo k. Now there exists the number 0 in the set of integers modulo k, such that for every element in the set of integers modulo k, we have that a plus 0 modulo k is the same as 0 plus a modulo k, and this is true as we have demonstrated that addition modulo k is commutative. And so this is the element r, where r is an element in the set z sub k, such that r is congruent to 0 plus a mod k, which is simply a modulo k. Now, as the element a is in the set of integers modulo k, we have that r is the element a, which is a plus 0 modulo k, or 0 plus a modulo k. And so the number 0 is the identity for addition modulo k. Now for every element a in the set of integers modulo k, there exists an inverse for that element, namely k minus a, such that a plus its inverse modulo k is the same as a inverse plus a modulo k, and this is the element r, where r is an element in the set of integers modulo k, such that r is congruent to the normal sum of a inverse plus a, which is k minus a plus a, which is k modulo k, and k modulo k is 0, or is congruent to 0, and so the element in the set of integers modulo k that is congruent to k modulo k is 0, And so we have that R is 0, which is the identity, and this is the sum of the element A with its inverse, modulo K, or also the sum of the inverse with the element A, modulo K. And so every element in the set of integers modulo K has an inverse under addition modulo K, also in the set. And so we have demonstrated that the integers modulo K together with addition modulo K is an abelian group. Now, since the cardinality, or the order, of the set of integers modulo K is the finite number K, the set of integers modulo K together with addition modulo K is a finite abelian group of order K.